Alright, in this video we're going to be talking about the exploration of data with tables and graphs. So in this stage of the game we have collected our data on a population that we want to understand, and we organize our data and we're presenting it in tables or graphs so that someone who wasn't related to the study would be able to look at our graph or table and be able to make judgments on the population without spending too much time or effort collecting data. The first table we're going to look at is a frequency distribution. So in the frequency distribution, we have a variable that we collected data on. We broke our data into classes. So in this case, we have 4 classes, 1, 2, 3, 4. And in each class, we tally up how many units of data fall into that class. So we're looking at our table. 7 people, or 7 units, fall into the range of 0 to 65 seconds. 15 units fall between 66 and 130 seconds. 20 people and 8 people, so on and so forth. So this gives you the class of our data and the number of units in each class. Relative frequency distribution is basically a different way of looking at the frequency distribution, except now it talks about percents. Percent is basically a representation of a part to a whole. So if we're looking at our data, it looks like if we did 7 plus 15 plus 20 plus 8, there is a total of 50 units. And if we're looking at our relative distribution, 0 to 65 seconds, we have 15%. That means we had 7 out of the 50 people fall into that range. And that's how they get the percents. They do the number that satisfies that interval. So we had 7 people in the 0 to 65 range, and there's a total of 50, which gives us 15%. And that's what they did for each one. And for all frequency distributions, the percents should add up to 100, representing 100% of the data. And last but not least, our cumulative frequency distribution. So in our cumulative frequency distribution, they go by class to class, and they basically add up the units. So our 0 to 65 range, we had 7 units. So less than 130 seconds, we did 15 and also 7, which gave us 22. Less than 195 gave us 20 plus 15 plus 7, which gives us 42. And less than 260 gives us all these units, so 8 plus 20 plus 15 plus 7, which gives us 50. Our next type of graph we're going to look at is a histogram. It's basically a bar graph that represents a frequency distribution. So on the vertical axis we're going to have our frequency, and our horizontal axis it would be our classes. So here from 0 to 5 we had an X number of frequencies. Let's just say that was, we'll call this 1, call this 2, 3. Okay, just arbitrary numbers just to get the point across. So, and the range in the class of 5 to 10, it looks like there was 2 data units. Let's say for 15 to 20, looks like there was close to 5 units. Okay? So a histogram is basically a bar graph that represents a frequency distribution. There's different types of histograms. There's a normal distribution. If it's normal, that means the graph will represent somewhat of a bell curve. Okay? It won't be, it's not always going to be perfect bell, but it will be closely resembling. There is a uniform distribution. Again, it's not going to be perfect every time, but if they are relatively the same level, that means it would be uniform. Skewed left, this is what gets people confused all the time because it looks like it should be called skewed right. But skewed left means that most of the data is going to be on the right-hand side, and there's not much on the left. So if it's skewed left, it looks like this. And skewed right would be the opposite, where most of our data is on the left-hand side. Another type of graph that we're going to see is scatter plots. Scatter plots are basically a representation of the frequencies of two different variables. So we have one variable here on the horizontal axis and a variable on the vertical axis. And we are plotting the relationship of these two variables in relationship to each other on a coordinate plane. Okay. These variables can have a positive correlation, meaning that if we plotted the points on a coordinate plane and it looks like a positive slope, that would be a linear positive correlation. And vice versa, if it was going downhill, it would be a negative correlation, negative linear correlation. And there's times where it's not linear at all, but there's still a correlation. That means it would just be a non-linear correlation. Then there's examples where it does not seem to have any correlation at all. So we plotted our data points and there does not seem to be any relationship whatsoever. And then there's times where we have a perfect correlation, which rarely happens in the world of statistics. We probably won't see one this year. But the two variables, the data points are plotted, and the points form a perfect line. So if we're looking at the correlation coefficient, this only works for linear correlation, our coefficient R will bounce between -1 and 1. It will never be less than -1 or bigger than 1. It will just bounce between these two numbers. If it is close to -1 or close to 1, that means it's going to be a very strong correlation. If it's closer to -1, it means it's a strong negative correlation. Closer to 1 means a strong positive correlation. If it's in the middle here, that means it's a weak negative correlation. This would mean it's a weak positive correlation. And if it's closer to 0, that means no correlation at all. So for example, if we had a correlation coefficient of, say, -0.9, that would be a strong negative. Or if we had, say, 0.87, that would be a strong positive. If we had 0.6, that's a positive correlation, but it's not that strong. Same idea for over here. 0.63. These are all just arbitrary numbers just to get a point across. So -6.3 would be a negative correlation, not that strong. And close to 0, so if we had, say, 0.14, that's a very weak correlation. Now we start talking about the regression equation. This is what it's going to look like. Y hat, that's what this represents, y hat. That means the predicted value of y equals some constant plus our slope times x. So if we are looking at, say, this correlation, all these points are data points that we collected. If we were to draw our correlation or our regression equation, it should cut our data roughly in half. Okay, so this line will be used to predict values of y. So say our variable, or a variable is time, and our b variable is money. And we are trying to represent the relationship between time and money, whereas if we spend little amount of time working, we don't have a lot of money, whereas if we spend a lot of time working, we get a lot of money. This linear equation can help us predict what we can make if we spend a lot of time.